Hello everybody, my name is Hunter Ream, and I'm going to be talking to you about Generating Functionology by Herbert Wilf. In particular, we're going to be talking about section 2.3, the calculus of exponential generating functions. The first thing that I want to talk about is a definition. So the symbol f with the bijection and an EGF written over the top of it, meaning exponential generating function, and then a sequence ranging from n equals 0 to infinity, means that f is identically equal to the series an over n factorial times x to the n. And so this is just saying that f is indeed the exponential generating function for the sequence a sub n. The first rule, we're going to call it rule 1 prime. The prime is because rule 1 was already used in this book for the ordinary generating functions, but rule 1 prime says that if f is the exponential generating function for some sequence, let's call it a sub n, ranging from 0 to infinity, then for h greater than or equal to 0, the shifted sequence, a sub n plus h, has an exponential generating function that is the derivative of f taken h times. So, as an example, consider when h is equal to 1. We want to find the exponential generating function for the sequence, the shifted sequence, a sub n plus 1, where n in particular is ranging from 0 to infinity. And I should note that in this rule, this is n ranging from 0 to infinity. Okay, so then that's why it's exactly a shifted sequence. In our example here, since n starts at 0, then the sequence itself is going to start at a sub 1, whereas the original sequence started at a sub 0, so we are indeed shifting it. Since f, the original f would be equal to the exponential generating function of a sub n, let's take the suggestion and see if the derivative does indeed work. So if I take the derivative of this, and just take the derivative, then we get that, well, if we take the derivative of the first term, it's going to be x raised to the 0. That's actually just going to go to 0. We can ignore that term entirely and just start at 1. And it's going to infinity. The first term is 0, so I'm not even going to write it. But the second term, we're going to bring the x down and subtract 1 from the exponent, as we would, just when taking a normal derivative. And now we have a cancellation that can occur. Since neither of them are 0, we don't have to worry about anything. We just get that the n here in the numerator, and one of the n's in the denominator, they'll cancel. We're going to be left with an n minus 1 factorial times x to the n minus 1. And it's good that the denominator and the numerator both have an n minus 1 in it. Why? Well, because we can re-index starting at 0 to infinity and just write a sub n plus 1 of n factorial x to the n. And just to compare, to convince you that this is indeed true, over here, if I put in my first term, 1, then the denominator is 0, the exponent here is 0. Okay, well, if I put my first term here, the denominator is 0 and the exponent is 0, and you'll see that this trend will continue. And similarly, the subscripts on our elements of our sequence are also going to line up. If we put in 1 into n here, then it starts with a sub 1. Here, if we put in 0, it starts with a sub 1. Okay, so that's good. So, and this is also exactly the generating function for the shifted sequence. So this does indeed work out, and that is great. So let's go to the next page. And so let's see if we can put this into action. So let's do another example, maybe one that's a little bit more enlightening. Find the exponential generating function for the Fibonacci sequence. So let's see if we can do this. Here's the solution. So we know that the Fibonacci sequence, I'm going to try to use explicitly as I can capital F's for the Fibonacci sequence. We know that it is generated using this recurrence relation. F of f sub n plus 2 is equal to f sub n plus 1 plus f sub n. And according to this rule, we can actually just take these, we can immediately come up with a generating function, but it's not exactly what we want. We recognize that this shifted element is shifted by 2, so we know that the corresponding generating function, if we say if little f is the exponential generating function for the Fibonacci numbers, then this recurrence turns into f double prime is equal to f single prime plus f. And this prime notation now, what this means is the derivative, what we would normally mean, right? F double prime, so you take the second derivative for this component, we take the first derivative for this component, and we don't take a derivative here. And so now we actually turned this recurrence relation into a differential equation. And that's really cool because we have a lot of tools to help us with differential equations. I'm not going to go through the tools that we would use to solve this, but solving this for f, we get that, what do we get? We get that little f is going to be equal to r e to the r plus, that's a subscript, times x, minus e to the r minus times x, all divided by the square root of 5. Where r, we'll just say r plus minus, I guess, is equal to 1 plus or minus, respectively, square root of 5 all over 2. And from here, we can just immediately come up with the sequence and the closed form, and from expanding these out using their exponential generating functions, which is almost immediately explicit, and then you just can equate the coefficients of this and get a closed form. So this was a lot faster. This was a lot faster provided we can quickly solve this exponential, or quickly solve this differential equation. Before, when we were doing with ordinary generating functions, what did we need to do? We needed to use partial fraction decomposition, and so I guess it's a matter of preference. In this case, I think it was easier doing this, but you can come up with your own opinion. Thanks for listening.